Building language modeling benchmarks is super hard because you got to get a few things right. You got to you got to work on a natural task that's interesting to a wide audience, but you also have to find something that's challenging for a language model, but still something that it can kind of achieve some reasonable score in. And you also have to make it something that you can automatically validate. There are lots of good ideas for benchmarks, but they're not really feasible. So anyways, all these benchmarks have all of these great properties. And I'm super excited to talk about them today. So the first benchmark that we're going to talk about, we're just going to do these in order of when we posted them to archive. So the first benchmark is called CiteME, and the speaker is going to be Ori Press, who's my brother. He's a PhD student in Germany at Max Planck in Tübingen. Okay, Ori, let's hear
Thanks for
yourself.
the intro. Is there just a place where I could read your thoughts about benchmarks in general, what you just said?
Yes, there's a blog post on my blog, Ofir.io, and it talks about all of these properties for benchmarks and why I value them and how I kind of read a benchmarking paper and what I kind of how I judge it and how I decide what benchmarks to work on and what to tell my collaborators. Yes, very good point. Okay, let's hear about SciME.
Thanks a lot. Okay. So I'm going to talk about CiteME. It's a paper I co-wrote with Andreas, along with Amer, Vishal, Ofir, and Matthias at the University of Tübingen. Okay, so when writing papers, scientists write statements that are supported by evidence. So statements that look like this. We evaluate our model on MNIST, LeCun et al., a dataset consisting of black and white handwritten digits. Now, we're basically saying what MNIST is, right? It comes from a paper of Jan LeCun. A normal paper will have tens of these citations per paper. So scientists do this often, and they do it pretty well. So scientists can do this, can back their statements up with relevant papers. And the question is, can language models do that thing? Can they, given some information, can they back it up with a relevant paper? And so let's test this out. Let's build a benchmark. Our benchmark is called CiteME. And we're going to try to answer this question. Okay, so basically, CiteME is made up of 130 questions, where each question consists of a text excerpt. So like the one we just saw, we took these text excerpts from papers, like famous papers, new papers, all kinds of papers. We tried to take one or two excerpts at max. And the goal is basically to find the citation, right? So we take these text excerpts and then we remove the actual citation, right? And so we have something like this. We replace the citation with the word citation. And the task is to basically to answer what is the name of the said paper? What did we replace? So for this excerpt, right, you would have the question would be the excerpt with the word citation, and the answer would be the title of the paper, which is this Jan LeCun paper. Okay, so on basically humans on this sort of data set, we gave humans that have expertise in machine learning 2 minutes to use whatever tools they wanted to basically solve 5 questions. We gave them 2 minutes per question, and they got close to 70% on this on CiteME. And we think this is a lower bound. We think that with more time, the numbers could even be higher. And the question is, okay, so what do the state-of-the-art language models get on this on CiteME? And the best language models get a measly 18.5% at max. It happens to be Cloud 3, Opus. Yeah, so this is basically, there's a 50 percentage point gap between the best language model and humans that only get 2 minutes, right? So it's a pretty big gap. And then the question is, what happens when we, let's say, give GPT-4 or any other language model the ability to search for papers and read papers, right? So humans, they could use any tool they wanted to, like Google or Google Scholar or Semantic Scholar, to answer these questions. And the question is, what happens when we give language models that ability? And so we built an agent. Basically, what it means is we connected, we gave language models a way to search for papers and read papers. And we called this agent Cite Agent, and it got 35.3% accuracy, which is a pretty big jump, right? It basically doubled the accuracy of the best language model. And just quickly, just to wrap things up, I think there's some cool behavior that this agent exhibits. It's a very simple agent, but it still seems to be insightful, I would say. Okay, so let's say, so the agent is given this question, okay? This is an excerpt, right? As we know. And it's not super important, the details about what's going on in this excerpt, but this excerpt talks about solving ImageNet using only local information. Okay, so we give this as input to our agent. The agent then says, has a thought. It says the paper seems to be about solving ImageNet using local information. And then it decides to search, and the sort relevance, it orders the results by relevance. It searches for the query ImageNet solved with local information. Okay, then we actually perform the search on Semantic Scholar, and we get the following results. It's actually, we get more results, but I cut it up here just so it's easier to read. The results are all kind of irrelevant. So the agent has access to like the title and the abstract. And so they're relevant, and smartly, the agent says, these results actually don't seem to be that relevant. And so it refines its search to ImageNet high accuracy using local texture features. And this is a much better search term. So now the results are much better. And in fact, the correct paper, the paper that we're looking for, is the second paper on this list. And again, so the agent reads these results, and it manages to say, oh, actually, the second paper seems to me pretty interesting. I'm going to read this paper. And then it says, I want to read this paper with this ID. And here we give it the whole paper. I cut out the whole paper, but we gave it the text of the full paper. And after reading the full paper, the agent decides to basically select that paper as its answer, and it's correct. Yeah, so the agent, again, this is not representative, right? So it does make mistakes, but it does seem that often enough it has good intuition about what the paper is. And yeah, it seems very promising. So if you want to learn more, if you want to get the data set, the code for the agent, or if you want to see more agent trajectories, as they're called, where it's a conversation between the agent and the system, please visit our website, CiteME.ai. Yeah, it has everything. Thanks for listening.
Okay, thank you very much, Uri. Excellent talk. Let's do a few questions. If you have a question, you can either raise your hand or you can just write it in the chat. I guess, can you tell us, you didn't really say, so you said language models get 18.5, but then you said the agents get 30. So when you said language models get 18.5% at first, what does that mean? How do the language models in that, what does that setting look like? How do they get 18.5%?
Yeah, it's just, we literally ask the model, like, here's an excerpt.
Yeah.
What do you think the paper it comes from? And then we have a setting where we give it an example. So we say, here's an example excerpt, and here's the paper that it came from. So in that setting where we have this example in the prompt, it gets 18.5%. It should be noted that our benchmark is kind of built to be hard for GPT-4o. So at first we collected a bunch of different excerpts, and then we asked GPT-4o to basically try to answer them. It answered about 40% of them correctly. And then we removed those excerpts that it succeeded on from the dataset. So the CiteME dataset, the 130 questions that we talked about, it's basically all questions that GPT-4o could not correctly answer in this zero-shot setting.
Yeah, so the setting that you're talking about is like a prompting only setting where you're just asking it, where is this citation from, or what paper is cited here, and you're not giving it access to any retrieval mechanism or any like web search mechanism. It's just the language model weights by themselves. And so somebody in the chat is asking a question. How much does GPT-4 get with a retriever, just a retriever, like so no agent, just a retriever?
How would that look like? What does that look like?
Yeah, I don't know. It would basically be an agent that only has one step where they can just do like a search for a query and then they have to select from that or something. I don't know. I think we didn't run any of those
Yeah,
experiments.
we had like a setting where you're only allowed to search for papers, but you're not allowed to read papers.
Yeah.
Yeah, you can look at more details in our results section.
And I guess that's not exactly RAG because RAG can only perform like one search, but RAG is kind of bad. You should just use an agent. Um, so somebody's asking, love this paper. Can you please elaborate a bit on the relevance of this? What capability really is it testing? Can this method be generalized to other issues? And somebody else asked if we've tested it yet on Claude Sonnet 3.5.
Yeah, so we're currently testing it on Claude Sonnet. We'll hopefully have the results out soon. The relevance of it, I think when you think about like having GPT-4 maybe come up with papers or paper ideas, a core step is being able to do literature review. So I think this is kind of like a first step in establishing how well these language models do in literature review. And I think apart from that, it's kind of like a cool test to do because basically when you try to figure out when you try to solve CiteME, you have to basically understand nuances between papers. So yeah, the task is basically to find the correct paper, right? But in order to do that, you have to basically differentiate between similar papers. You have to pay attention to certain details that are mentioned, for example, in the excerpt, and make sure that they match the paper that you're that you picked. Yeah. So I would say that there's one very clear like direct thing that we're impacting, which is maybe like research assistants and helpers. And the second thing is just I think that there's like this indirect evaluation of how well your model can understand papers and nuances and details in papers.
So Benedict asked, how much more expensive is the agent versus just the prompted model? The agent is much more expensive, probably, right? It's in the paper, but
yeah, we have the exact breakdown of the costs in the paper. I think it's a bit more expensive. Yeah,
it works like twice as well. Okay, Mingyang, can you share your screen, please? Thank you very much, Uri.
Thanks a lot.
Talk. Mingyang.
Yeah.
So Mingyang is from UIUC. Yeah, we wrote this paper together with Hao, who was in the PhD with me, which is really great. And now Hao is working with Mingyang too. So it's super exciting to be part of that collaboration. Yeah, take it away, Mingyang.
Yeah, sure. Yeah, so yeah, today I will talk about some details about like the SciCode. It's a new research coding benchmark that's we released recently. So it's focusing on the scientific tasks on the natural science domain, and we've collaborated a lot of natural scientists to develop and annotate this benchmark. I can give a quick or simple example from our development set, which is the icing model. So the general question is that like find the transition temperature of a periodic 2D icing model with metropolis Hastings algorithm, and the coupling constant J is 1 and the X without any external magnetic field. So this is a very simple and classic problem in the StatMac domain. And basically what we want to find is that, so we can see this phase transition plot here. The x-axis is the temperature, and the y-axis is the magnetization. And when magnetization is 1, it means all of the spins in the grid are aligned. And when it's approached to 0, it means it's more randomized. And as you can see from with the increase of the temperature, it will transit from this state from like the same similar spin to a more randomized state. So and there's a lot. It's a well-studied. Like the critical temperature is around like 2.269. So that's what we want to reproduce. And given this problem, what a scientist will do is like to first calculate the total energy given the system Hamiltonian and the system state. And then we will sample the distribution of equilibrium states using the Metropolis-Hastings Monte Carlo simulation given a temperature. And then we will sweep different temperatures to find the transition temperature. So we've basically separated those steps into several multitasks from 1.1 all the way to 1.9. So we for this Ising model general problem, we'll have 9 sub-problems. So why we are choosing Ising model is it's a very, although it's a simple and classic, but it's still attracts a lot of people's attention, like in even like frontier research, because it inhibits complex behaviors. It's very crucial for researchers in the different domains like StatMac, material science, biology, and mathematics. So a lot of frontier researchers are based on this prototype for many complex systems. So one direction is to like further augment this Ising model. Then, for example, we can change from the 2D square lattice to a triangular grid for frustrated configuration. So the problem will be a lot more complicated. And the Ising model is also a kind of a critical behavior of many more complex models like the liquid gas models or a lot of others. So you can see from this point, like how we are selecting problems for SciCode. So they're all sourced from scientists' real research and the practical needs. And we've concluded that they can be numerical methods, simulation of systems, or different scientific calculations. And for each general problem, we make sure it is verifiable with publications or theoretic models. Since SciCode is very challenging because it's a kind of a mixture or naturally blends the scientific knowledge, complex reasoning, and coding capability. So as you can see, like for the state-of-the-art model, which is the Cloud 3.5 Sonnet, the main problems is only the accuracy is below 5%, which is around like 4.6. And for the sub problem, it's a little bit higher, but it's still a lot of to improve, which is the best model achieves about 26%.
Just quickly, meaning how many problems do you have in the whole data set and how many sub problems?
Oh, we have about like 280 sub problems and 80 big problems.
Thank you, yeah.
Yeah.
Wait, do you want to go to the next slide or? Oh yeah.
Yeah.
Oh, is that
So
it?
Oh, that's it. Yeah.
Oh, is that it? Okay, so we can start questions from the audience.
Yeah. I'm seeing like for the sub problems, I mean, like,
Okay,
for
good.
example, like for Ising model, this is find the transition temperature is the big problem,
Yeah.
but we can, like but it can separate to, 9 smaller functions, which they work as a whole to solve the whole problem. So like for this big problem, we have 9 sub problems.
Yeah. So somebody's asking what a subproblem is. I think Mingyang just explained it. There's like these big questions that are split into sub questions. And so the sub questions are easier, so the models get a larger percent of them correct, but the big questions are really, really hard. So state of the art is really low. And I guess I'm asking you questions that I know the answer to, but some people might wonder. So there's a tough question. Can you go back to the question? What is expected of the model in order to resolve this question? Like, am I expected to give you a number or a bunch of words or code? What's the
Oh,
solution?
yeah. I think like in SciCode is a little bit versus it can be a number or it can be an array or a list. I think we have different kind of
No, but
uh,
like I guess what I was trying to say, SciCode is about code, so all the answers are you have to produce code that will produce the answer.
yeah.
Um, and then how do you check my code if I'm a language model and I'm submitting a code? How do you check if it's correct or not?
Yeah, so like for each sub problem, we'll have like 3 numerical test cases. And if like the language model or the model generated code can give like the same output, then we consider like this subtask is correct. And yeah, so like for the general problem, like we also have like 3 numerical test cases. We also have like the domain specific cases. For example, for this one, we want to see whether it can reproduce the number in the paper, which is the critical temperature, 2.269.
But basically, the bottom line is SciCode is extremely tough. Physics, programming, and biology, and lots of other fields that you can see in the paper. It's extremely, extremely tough programming challenges that you need like a PhD to solve. And then we ask the model to write some code. And then we have a lot of unit tests that were also written by PhDs or above to make sure that the code that it wrote was correct. So it's extremely natural questions because none of these questions are just Mingyang sitting around thinking, oh, how can I ask a tricky question to trick a language model? All these questions are based on real papers that were published in real conferences by like real physicists. And we're just trying to see if the language model can kind of recreate the logic behind these physical phenomena. And then we have these unit tests that test these language models really well. So if you got it right, we don't care how you programmed it. If you got it right, we're going to detect that. And if you got it wrong, we're going to detect that. Do we have more questions from the audience about anything in this paper? Okay, Mingyang, we have a question. Oh, wait, this is about SciME. Wait, let's do questions about Mingyang's paper, and then we can talk again about SciME later. Oh, no, this is not about SciME. So the question meaning is, could an agent do better on this? So you said that we got 5% here. So with CiteMe, we showed that initially we got 18%. We wrote an agent, we got 30% or around that. So could you build an agent that could do better on this data set?
Yeah, I do think so, because so at least like because it's not only about like complex reasoning and the coding capabilities, it's also about like it has some like scientific knowledge like in that. So sometimes we observe the model it's like this getting it wrong. It's because of like the kind of knowledge it's kind of integrating into its code is incorrect. So I think at least for this case, I think agents will help a lot on this part.
Yeah, I think one of the things I've noticed with agents, so the difference between an agent and like a direct prompting approach is that with direct prompting, you give a model question, and then you give it one chance to program it. And if it got it right, it gets it right. If it not, it's over, right? With an agent, you can have a possible solution. You can let the agent test it itself, and then the agent can detect some bugs. It can try to iterate on it, and just iterating leads to much better performance. So I'm sure that Minyang is right, and an agent would do much better on this. But because this task is so hard, I assume that an agent would go from 5% to 10%. I don't think agents are going to solve this because there's just a lot of knowledge that's needed here that language models don't yet have. But I'm sure that part of the solution, part of the system that will actually get a really good score on SciCode will be to make it agentic. One more question. You can raise your hand, or you can. Somebody's asking, this seems like a task like SWE-bench. Yeah, this is kind of like SWE-bench, but you need to know a lot of physics. How much will long context models and pre-training, instruction tuning, and synthetic reasoning I don't know. Yes. As we get stronger models that are trained on longer segments of code and get better reasoning, we're going to have better models on SciCode. Okay, last question. Does anybody have a last question? Okay, Oriolan, let's hear about AssistantBench.
Okay,
And we'll
thank
stay
you.
here afterwards so everybody can ask more questions. Okay. Next talk is about AssistantBench by Oriolan. Oh, thank you, Minyang. Next talk is by Oriolan, who's a PhD student at Tel Aviv University. Let's go.
Hey, everybody, can you see my screen and hear everything's okay? Great. So thanks for inviting me, Ofir, and great to be here. So I'll talk about AssistantBench. And this is a work with great researchers from Tel Aviv University, UPenn, AI2, and of course, Ofir from Princeton. So first thing, what is AssistantBench? So basically a benchmark for evaluating web agents, but on tasks that are realistic and time-consuming for humans, and it can be automatically evaluated. So let's look at an example. Let's say I'm an early bird who likes to work out, and I want to know which gym near Tompkins Square Park has fitness classes before 7 a.m. So to solve this task as a human, I would first need to find all the relevant websites. So perhaps interacting with some kind of map tool to find the list of websites. But then I will need to go through each website and actually interact with it to understand when are the earliest classes. So for example, go to the website of this first gym and see when are the earliest classes, but actually do this for all these websites. I need to be able to interact with many websites and reason over them and then aggregate the answers. So this is obviously very time consuming for humans. So why do we want to focus on tasks that are both realistic and time consuming? So basically, there are dual reasons that complement each other. So one thing is that if it's realistic and time consuming, it will be extremely helpful for humans if you can have an agent that solves them, right? That's how the task that we solve most times for humans. The other thing is that if this is time consuming for humans, it's probably very tough for agents and it can be really good as a task to evaluate web agents. So how can we collect these kinds of tasks? So basically, we can just go and ask humans, when did they recently have tasks that were time consuming but were solvable on the web? So for example, somebody who again is an early bird who likes working out might have had this kind of task, but a different person might have been interested in movies on Netflix with specific actors and specific ratings. So by asking different people, we can get a diversity of tasks. And once we have these tasks, we can use crowd workers, take these tasks as templates, and create similar tasks. So for example, if we just change the name of the actor to a different actor, and Netflix to Voodoo, we get a different task about Isabella Gianni. And similarly, if we change the conditions to be from gym to bars that are wheelchair accessible and the location, we'll have a different task, and this way we can scale our data collection. But the problem with this is if we have diversity, we can also reach the domain expert and annotator and ask them to choose tasks from their specific domain, which will increase the diversity of our dataset. So once we take these three approaches, we get to more than 200 tasks, but that are very, very diverse. So we want to maximize diversity. The tasks come from over 50 different people and reflect real user needs across domains and scenarios. And the other nice thing about this task is that it can be automatically evaluated. So we focus on tasks that are not time dependent. Either they have static answers, so with specific date constraints. So if we know the highest price for an apartment in a specific area, this will likely stay constant. And the other criteria is the task must not be time dependent for at least a year. So for example, business times can change, but it doesn't happen very frequently. So we can keep this task in a live evaluation for the near future. It will also be very easy to monitor this and reannotate if needed. We can actually use the entire web as our environment, and with this kind of stuff that are not time dependent. So what is the performance of current systems? I think everybody who works with this kind of web agent knows that they tend to be pretty bad once things get complex. So existing agents get under 5%. This is CX, which is a state-of-the-art agent, which gets 4.2. It's actually only able to generate answers 20% of the time. So if you just take a closed book model, which basically has no access to the internet and just guesses the answer, it has a very high answer rate. It always guesses, but its accuracy is also pretty low at 22%. So how can we make progress on AssistantBench? Well, the easy answer is just let's build better agents. So we also introduced CPlanAsk, which is a variant of CX, but we had two specialized components. So one component is to transfer information between steps. We just ask the agent which information to pass on. This is what you can see here as step 2. And the other component is just to plan and replan the execution. So based on the current screenshot, what should be the plan going forward? And we see that SPA really increases results. So it increases accuracy by 7% from CX. But the nice thing is that it increases coverage and precision. And once we mix SPA with the high coverage of closed book models, we get to the best overall accuracy, which is at 25%. So what's next for AssistantBench? There is plenty of room for improvement. So 75% to improve. And when we do an error analysis, we find that the majority of the errors are due to this difficulty of web interaction. So either navigating the web or grounding to the web environment. So there is plenty of space to work on better agents. And the data is already available on Hugging Face. You can just download it and start working. So to summarize, AssistantBench is a benchmark for evaluating web agents on tasks that are real, time-consuming, and can be automatically evaluated. We already have an agent that improves performance, but there is plenty of room for improvement in developing new agents. And thank you for listening. I'll be happy to answer any questions.
Thank you so much, Ori, for the great talk. We have one question. What's the ratio of information-seeking tasks and action-based tasks? For example, writing a comment.
So all tasks are info-seeking. That's how we allow for the automatic evaluation. So because, like if you're familiar with Web Arena, if I remember correctly, it was one of their contributions of let's have tasks that the way to evaluate them is based on the final answer. And then you really don't care, as Ofir said, like agents can try something, go back, try something different. But the only thing that you care is if it reached the final answer or not. So that was our design choice. But I think that it's also great when working on web agents that actually you evaluate them based on their action, but it's not the focus of this work.
Yeah, I think it was a good decision to focus on like this information seeking stuff. We can have like extremely hard tasks, but it's very easy to evaluate. Alyssa Liu asks, did you also evaluate SPA, which is our agent, on other agent benchmarks other than AssistantBench?
Yes, so this is a great question. So we actually wanted to, but there aren't too many web tasks that are like this. So what we did use is we used Fanout QA, which is a data set, but for question answering tasks, but over Wikipedia, but it requires sending out like from a table to multiple sites. So it's like something about finding the table about GDPs of countries and then finding information about each country. So this is a great actually development set for us because it's exactly what we want for SPA, right? You need to go from one website to another website, give some information, then plan what you need to do next. And we actually see huge gains between CS and SPA, more than what we see on AssistantBench, if I remember correctly. So that's with our two settings, basically like you can go with like only Wikipedia, but very complex question answering tasks and AssistantBench. But it will be great to test it on. I think once people work on more data sets for web agents that are very, very complicated, it will be great to evaluate that. And probably, as we said, like there is a huge area to develop even more complicated agents that will be great to evaluate it on a bunch of benchmarks.
Okay, do we have any final questions for Ori before we talk about SWE-bench? Are you sure that the answers are up to date, Ori? Last question.
Yes, so we double checked it. Each question was verified by at least 2 authors. It's all up to date. As I said, it's very hard. Like it's a fine line between working on live environments that can change and keeping them up to date. So we made a huge effort, like at least 50%. We're sure it's static. It's not going to change. The other 40%, like we can't guarantee, but we are very, very optimistic that it will be like this in the next at least a year. And we also made a lot of efforts to re-annotate. We have all the trajectories, we have all the goal strategies. So the answer is basically, and we'll make it very easy to rerun all our agents. So you can always compare. If you have 2 systems, you can always compare between them. So we're really optimistic that we made a huge effort, that as much as possible. But of course, like each time, this 40% of questions, they will change, and then we'll need to either re-annotate or just rerun the agents that you want to compare.
Yeah, thank you so much. Yeah, I think AssistantBench is super, super exciting. We had CiteME, which I think is going to be super helpful for researchers, both right now and like when I'm writing papers, I really want an assistant to automatically tell me which papers to cite or to verify my claims. And then we had SciCode, which is going to be very helpful for physicists, but also going to make language models like much better programmers and much smarter overall. And then AssistantBench is just something that's been bugging me for a long time that, you know, if I want to ask Google, give me like a restaurant that's near me right now that has entrees for under $25 that has like, you know, soy-free and gluten-free entrees because I have a lot of dietary restrictions. So it's something that I'm constantly bumping into and Google can't do that. And it can't, you know, find me a yoga studio with classes before 7 a.m. near my house that has like a vinyasa teacher or whatever. So I think AssistantBench is something that's really important for language model system developers to work on. And so those are 3 new benchmarks. We've put the websites, they're all out. You can use them all right now. We've put the websites in the chat. And now we're going to briefly talk about SWE-bench. And then we'll talk for a minute about Ofir's Gelato challenge. But first, let's talk about SWE-bench updates. Do you guys want to join me here?
On that side?
Yeah, come.
Sure. Well, that's gonna be cozy.
Yeah. How do I pin this? Oh, there we go. So let's see if we can fit in frame. Are we getting this? This is like, there's hundreds of people. There's a billion people. Oh, dude, my camera's
Just a smudge.
Oh, dude. Sorry about that. Sorry. Oh, there we go. Oh no, it's just okay. This is Carlos. And this is Alex. He's the second author of SWE-bench. And
Sure.
we're very, very tightly packed here. Carlos, tell me about SWE-bench Dockerize that we put out. And this, like, I told people this would be over in like 5 minutes, so you have to be very...
Okay, it'll be fast.
Okay, what's SWE-bench Dockerized? We put this out like a month ago.
Yeah, so SWE-bench Dockerized. So when we first built SWE-bench, we were really just like you know, getting it to work on our own system.
Yeah.
We didn't think, I mean, we thought about trying to make it portable, but I think that some people definitely had some issues there. And so there were a few efforts that, like, once SWE-bench kind of was public and other people were trying to use it, there were some efforts to try to move our evaluation system to something that was more portable, where like every instance had its own Docker image. And essentially we ended up working with like some people at OpenAI reached out to us, and they kind of set some of the basic architecture up. And then John and I actually coded up a lot of the, like, we ended up making it like the kind of final product that people that's there
Yeah.
right now. But essentially, yeah, like the basic idea is that we just made it so that the setting up SWE-bench evaluations was a lot more portable on different systems,
Yep.
and could be run on like any computer.
Yep.
And hopefully, yeah, it'll make it easier to scale them. Yeah.
SWE-bench is like so much easier to run. If you wanted to play with SWE-bench, but you tried it out like 2 months ago and you couldn't get it to work,
Yeah.
try again. It works really well right now. I mean, it's not perfect, but it's
It's
much
pretty good.
easier to use.
Yeah, it's much better
Okay.
to use.
So that was SWE-bench Dockerized. That came out like a month ago.
Yeah.
Tell me about, I was browsing the web and I happened upon the OpenAI blog
Okay.
and I saw this blog post about SWE-bench Verified. Can you tell me about that
Yeah.
in 30
In
seconds?
30 seconds. Okay.
Yes.
So SWE-bench Verified, it's essentially what some people at OpenAI were interested in was getting they first were interested in like kind of analyzing all of the problems in SWE-bench and like
Yep.
what kinds of skills it was testing on, and the problems that were there. And I think the general, like when we first, just as a result of kind of how we scraped it, I think that there are some issues with SWE-bench instances that are very like they're related to the skills, but they're also very influenced by, say, coding style, or like, say, the tests are very maybe constrained on particular like wording of error messages, or like, I don't know, like when you write a unit test, you could write unit tests that are maybe over specified for your problem, or like for your solution or something.
Yeah.
And so they were kind of interested in like filtering out examples like that. And it's very like there's thousands of instances in SWE-bench, and so it's kind of expensive to do that. And so what they did was just take a big subsample and then try to filter that subsample to get a subset that they thought is very like, that just tracks very closely with like human abilities. And so like presumably the upper bound on SWE-bench, like the whole SWE-bench subset, or the whole SWE-bench data set it's definitely not 100. Like there's probably some instances that are way too hard, but on SWE-bench Verified, it should be closer to 100. Like a smart person, or like a person like an expert in like these data in these repositories could presumably, like answer or like submit a pull request that could pass all of the tests.
100%.
Yeah.
Yeah. So basically the way I see it is in SWE-bench, we automatically crawled it. So a lot of the by the way, this is being live streamed to Twitter, like
Okay.
the desktop.
Okay. Yeah. Okay.
So we built SWE-bench, we crawled it automatically. And so when you crawl a data set automatically, you just end up having bad instances here and there.
Yeah.
It might be 5%, it might be 15%, but some of the instances in SWE-bench are bad and they're just never, ever going to pass,
Yeah.
which is totally okay. But the OpenAI people wanted to have like a small subset where they would know that the maximum achievable pass rate is 100%. And so they put out the SWE-bench Verified, but SWE-bench Verified is not all of the instances that could pass. It's just a subset of them.
Yeah.
And we've already seen that it's a pretty conservative subset. So there's a lot of issues that have already been solved by a system that's out there, but they're not in SWE-bench Verified.
Yeah.
And so I think going forward, people should still keep on using the full SWE-bench test set or Lite if you don't have enough money to run the full set. And then I would just use the verified set when you're doing analysis to kind of try to figure out, when you're like, after you've already built the model and tested it on the full test set, use the verified set to look for like, okay, this issue should have been solved by our model, but it wasn't solved. what went wrong here. So you could totally do that with a verified set, whereas with a task that's in a full set, some of them are just unsolvable. So you could try to figure out, hey, why couldn't we solve this? But like, it's actually unsolvable. So you might be wasting your time.
Yeah.
Okay.
I also think it gives a good sense of like we're still even unverified, like the performance of these kinds of
Yeah, it's
systems,
40%.
it's not like super good,
Yeah,
right?
yeah.
And so I think just as like a barometer for solving the simplest types of bugs, like a system should be getting really high scores if it's good
Yeah,
at it. So
yeah. I think that's, do you have anything else you want to say about Dockerized
They
or
do some
verified?
analysis as well, right? For like
Yeah.
how long it takes human
Yeah,
programmers
exactly.
to solve SWE-bench issues, which is really
Yeah.
interesting. Do they release that data as
Yeah,
well? or
yeah, so
just,
they do. Yeah, I think even like the performance, so they have like essentially kind of difficulty measures like as part of their annotation process, which was really cool. And I do think like in a way at the margins, like the difference in score between like 90 or like I don't know 80% on SWE-bench verified and like 85 is actually going to be those hard issues, and that'll be very indicative. I think even as SWE-bench becomes more saturated in like a year or so, um, the marginal kind of performance boost will actually be kind of meaningful.
Okay, we can do a few questions before I'll close this off by talking about my gelato challenge. Somebody's asking, do you have any thoughts on how you'd update and scale SWE-bench verified, given the amount of human
Yeah.
annotations required to produce this?
Yeah, I think we want to do so it was definitely insightful thinking about how like the types of problems that SWE-bench verified filtered out or in. I don't know if I have a great kind of takeaway on how exactly to do how to scale this kind of annotation process. Although I do think there are definitely some kind of general lessons to take away from that process. And so like in the future, if we do more like data sets or whoever does data sets, I think can like look at SWE-bench verified a little bit to think about or like inspiring um for inspiration on like building filtering criteria or trying to build, you know, a data set that's still hard, but also not, you know, not too difficult.
I'm actually like, it took them a lot of effort. It's very clear from the blog post that it took them a lot of effort to filter this out. And I don't think that the return on investment there really matches the amount of effort they put into it. Like
Yeah.
they had a data set which was maybe 85% good, and it took them a lot of time and effort and money to go to a data set that's like maybe 100% good, but like, so what? Like I think it's just totally fine to have a data set that has some faulty issues in it. And I think what we did with SWE-bench Lite is really cool, where we automatically tried to filter out really bad issues. And I think we did a pretty good job over there. So you can automatically filter out bad issues by like trying to see if an issue like has like less than 5 words or more than 500 words, or there are all kinds of automatic things you could do to try. Or we kind of noticed that if it edits more than 3 chunks, it's hard, or if it links to like a different issue, it might be like too hard or complicated. So
I mean,
there are things you can do
it's
automatically.
worth saying as well that it's the OpenAI preparedness team that did
Yes.
this. So
Yeah.
they're primarily interested in like sort of estimating when AI systems are really approaching human proficiency in these expert tasks.
Yeah.
And that's a very different use case than like what we designed SWE-bench for, which is sort of comparing models, right? And actually like as like a sort of software engineering benchmark for models.
Are you guys looking into iteratively creating data sets from failed executions?
What do you mean by failed
I
execution?
have no idea, but maybe
What is failed execution?
I don't know. What is failed executions, Julian? You should tell us, and then we'll be able to answer.
Just the agent didn't get the issue.
Like adversarial?
Oh, like filtering adversarially, like only really hard issues.
That's possible.
Yeah,
you could try
you could do it. You could.
Yeah, you could do like adversarial SWE-bench. I think that'd be interesting.
Or maybe, you know, fixing the wrong solutions that agents put in. You don't give it.
Oh, like human eval-fix or whatever. I mean, when we first put SWE-bench out, the solve rate was 1.96%. And so you could kind of say that it was a data set that, you know, agents failed on 100%, or like the best system. It was kind of an adversarial data set because the best system at the time got basically like 0% accuracy. But we haven't really done anything on that recently.
One more question.
People are asking about like other SWE-bench variants. We don't have anything to talk about right now on that. Anything else before we leave?
Tell us about your gelato challenge.
Oh, Ofir's Gelato Challenge. Yes. Okay. So we're going to close this off. Oh, you haven't heard about my Gelato Challenge?
Ofir's gonna hand make gelato at home, burn it himself.
Wow, we lost a lot of people. Like a third of our audience quit because of SWE-bench verified questions. So we're gonna have to. Anyways, Ofir's Gelato Challenge. I think I have this. There we go. Can you guys see my screen? Yes. Did you see this image, Alex? So Future Gelato Challenge at New Rips, which is coming up pretty soon in December. I am going to buy gelato for the team that has the highest combined score on these benchmarks that we talked about today. So Alex, oh, you can't compete because you're part of SWE-bench, but if you weren't part of SWE-bench, you're invited to compete. You just need to show me your score on SWE-bench Lite, AssistantBench, CiteME, and SciCode. And whoever has the highest score, it's got to be pass at one. There's all kinds of rules here, but they're pretty sane. And I will buy you gelato. But if you have 1,000 people on your team, I will have to reach out to the trustees of Princeton University to figure out how much of the gelato they'll cover for me. And I'm only buying as much gelato as Princeton will reimburse me for. So
You're
everybody
hedging your
everybody
bets.
gets. How about you have everybody like
get like a spoon of
get
gelato?
like the
Yeah.
sample, the free sample of
Yeah,
gelato.
exactly. You know what? Yeah, if you have 1,000 people on your team, you can come and get a free sample, and I'll watch you get it. But that's it. I'm very excited about the Gelato Challenge. I'm really looking forward to somebody building a system that can do well on all of these things.
It's
And
pretty cold though in Vancouver.
in Vancouver, I didn't think of that. I'll also, you know, we might be able to swap it in for like a tea, a hot chocolate challenge. Yeah, I didn't think about the coldness aspect, but that's good. Okay, any final questions before we wrap this up? Okay, everybody, thank you so much for coming. We're all on Twitter, on X, whatever, email. We got snail mail. You can send us to the Friend Center at Princeton University. We're right by the Princeton University Press. So you could also mail them a letter, see if they could, we share a parking lot. You can mail them and they can transfer it over to us. Thank you so much for coming. And hopefully we'll do more of these types of events. Thank you so much, everybody. Bye-bye.